wrong screen. There we go. Oh, okay. Minor details. Hmm?
The dongles.
Yeah. Well, yeah, the whole thing is not connected. Yep. Most of our classrooms still only have VGA connectors, even though most computers now are HDMI. So the equipment that we run is a little bit outdated. All right, the streaming is already on. Okay, you cannot see the little green square. Now we can. Okay, so we are already streaming. The audio is good. And what we'll do today, okay, first thing is to remind you guys when our final exam is going to be. This is a Monday, Wednesday class, and our start time is 10:30. No, yeah, it's a Monday, Wednesday class. So we are in this particular time slot. This is the range of start time, because we are starting at 10:30, um, and this is a Monday, Wednesday class. So that means next Wednesday, on the 18th, is our final exam day, and then the exam time is from 10:15 to 12:15. So just kind of make a note to yourself, because the start time of the exam is 15 minutes earlier than the usual lecture. So if you're used to going, coming here by a certain bus, and the bus schedule, will get you here on time at 10:30, you need to make an adjustment to that, so that you will be on time here. Is that okay? All right. So once this is out of the way, what we'll do today is to take a look at the exam last semester. So this is a review of the final exam. And let me go find it first. Let's see. There's one. Not sure. Yeah, this will work. But this is only a year ago. Let me see if I can find one from last semester. Yep, there's a whole bunch. Oh, wrong program to open it. There we go. All right, so this is the exam from last semester, which is the closest we can get, to this semester. It's open book, open notes, just like with the first two exams. So you make sure that you bring all the material, that you want to bring with you. That's either handwritten or printed prior to the test. Okay, so you can bring in anything. Okay, all the sample programs that we talk about in this class. Okay, the Fibonacci program that I gave you as a solution, and of course I will also give you the solution of the homework that is due today. So the tree program will have its own solution as well, and you're more than welcome to print those programs out and bring that with you. Okay, the entire ROM content you can bring with you. Just basically anything. Okay, there's no limitation of what you can bring with you, um, as long as it is printed or handwritten prior to the test. So are we good with that? Okay. You can also bring a scientific calculator if you think that you might need a scientific calculator. You can bring one with you. A graphing calculator is fine. I really doubt that you will need any graphing capability. But if that's the only calculator that you have, or you want to bring that with you, that's certainly okay as well. So are there any questions about what we can or cannot bring or use during the final exam? It's pretty much the same stuff as the first two exams. Okay, I just want to re-emphasize, that you cannot listen to music, okay, with a headphone, during the exam, because some people like to do that, but I think it's probably a better idea not to let people do it. All right. So this is the first question, well, it's not the first question, but the entire final exam last semester, basically a few questions revolve around this code. So the code has kind of the very similar stuff that you have dealt with already in the homework assignment that's due today. So we have a node, but this time a node does not have 2 pointers. All it has is 1. Okay. So we have value as a field, just like the homework assignment that you turned in earlier today. But instead of having left and right, it only has n, and n in this case stands for next. Okay, this is how it points to the next node. So I'm just explaining the C code right now. We have some prototypes defined here. We have node init, we have node append, node atList, node D, C, B, A. So those are all basically predefined like this. And this is the main program. And over here, you're given this assembly code. So the assembly code that you are given with is the beginning of this part here. Okay, these 3 lines, node underscore v, node underscore n, and node underscore size, are defined basically just to let you know what is the offset from the beginning of a structure to the members v and also n, and also what is the number of bytes that one node needs. That's node underscore size. So the definition of those 3 labels are consistent with what we have already talked about in this class when we talked about structures. Do we have any questions about the first 3 lines in assembly code? Nope. Okay. So we have a no op, just because I wrote this so that we can run it in the command line version of the simulator. And then JMPI main means main is defined somewhere else. Okay. So this way I don't have to make main the first thing in the entire program. So now we have node DCBA. Okay. So node D, is initialized with 1, 2, 3 as the value, 2, 3, 4 as the node, and then node C is defined as 8 as the value, and then a null pointer as n. Node B has 2 as the value and 0 or null pointer for n, and then node A has 5 as the value, and then node B being the second item, which is the pointer to the next node. Okay, so that's how it's defined. You can see this is actually a simplified version, or it's a simpler version of what you have to work with in the homework assignment that was due today. So are we doing okay so far with this code? Okay, just the assembly code and also the structure itself, the structure definition itself. So here comes question 1. Question 1 is asking, assume that you're given the following code, you need to perform 2 tasks. On each line that changes a register or memory location, use C constructs to explain the operation and, if applicable, what is being updated. Okay, most likely which register is updated or which memory location is updated. When register D is changed, indicate the following, the corresponding stack operation. Are we pushing? Are we popping? What are we looking in the stack when register D is changed? Then decompile the following code into structure C code. Do not use any goto, break, or continue statements. If conditions can be combined by Boolean operators, if they can be combined, combine them. So I'm looking for conjunction, disjunction, negation, that sort of stuff in the conditions. So this is node append, which is one of the subroutines. So the prototype is already up here. If you look at node append, this is the prototype. And when you look at the actual assembly code, that's the assembly code. So make use of the prototype, because the prototype will clearly indicate what kind of parameters the subroutine can expect to be on the stack already. That will give you, an idea of what are we accessing on the stack when we perform a particular operation. Okay. So I'm going to answer this question using the tablet mode, because this way I can draw pictures and it is going to be resembling what you will have to do to answer this question. Okay, so I'm going to do this one just as I said a little bit earlier. So the first thing we need to do is to understand what is on the stack. According to node append, we have p as a parameter, as the second parameter, and then we have pp, which is a pointer to a node, being the first parameter. Okay, so what we need to do is to draw a picture of the stack first. So we have parameter p, and then we have parameter pp, and then the return address on the stack.
So even though we haven't seen it being called, we should that's there on the stack.
Yes, because you want to know when the subroutine executes, what can you assume on the stack.
Okay.
So that is why you need to have a picture of what the stack would look like when this subroutine has control. Okay, so the first thing we do is then we basically say this is the last thing that we push on the stack, which is where register D should be pointing at. So with this information, now we can go ahead and comment on each line of code. So this is the first one. Which register is getting changed, and what happens to that register? What is the meaning of that register? So if somebody says oh, A becomes the same as D, that is not worth any points, because you're just explaining that answer is really just explaining what CPR does, but it doesn't give me any. It does not indicate whether that person understands what is on the stack, which is the purpose of the question. Okay, so in this case, what I would do is I'm going to say, as a result of this, A is now the address of the return address. Okay, is that okay? Are we good? Okay, so what about the next statement? If I add 1 to register A, and register A basically was pointing to the same place the register D was pointing to, so that means now it is the address of parameter pp, which is the first parameter of this function. So now we say register A is the address of pp as a parameter. Is that okay? Are we still doing okay so far with both the notation and also why register A currently has the address of parameter pp? Okay. And what about now? Okay, register is not getting changed, but register C is getting changed.
C now holds PP.
Yep, C is parameter pp. And this one doesn't really do anything. Register C itself is not modified, but we are testing register C. Yep. So this can influence, the Z flag and also the sign flag. But it doesn't change any of the other flags. Okay, the carry flag is not affected by this. The overflow flag is also not affected by this. And the next one says JZI to end if. Okay, so the label itself in this case clearly, it spells out what kind of control structure we're dealing with. But we are not, at this point, we are not too concerned about the conditional branches, so we'll save this for later. And what about now? Increment A. A still has A still had, before this instruction, it still had the address of pp. If I add 1 to A right now, what would be in A? The address of parameter P. Very good. So at this point, A is going to have the address of parameter P. And since we're dereferencing it, so that means A is parameter P at this point. And then when we get here, we're storing parameter P to where C is pointing to. Can someone remind me what is in register C itself right now?
PP.
It is pp, the parameter pp. Okay, so that means what this statement is doing is we are dereferencing pp. Whatever pp is pointing to, we are now going to store whatever p has. Are we good so far? Okay. And what about here? I didn't change the stack pointer at all. If you look at register D, it never got changed, throughout the execution of this code, which means register D at this point is still pointing to what? The return address. Very good. So to be safe, I'm just going to say at this point B, because we are not changing register D, so you don't have to tell me what is in register D. But because we're changing register B, you have to tell me what is now in register B. So register B now has the return address, not the address of the return address, but the return address itself. And now the stack pointer points back to the address of the first parameter, which is pp, and that's it. So this is the kind of documentation or comment that I want you to do with a question like this. In other words, I want you to look at the assembly instructions and tell me how that correlates to the C code. Okay, what parameter are we accessing? Which register has what in C concept? Does it have the address of a parameter? Does it have the actual parameter itself? Does it have what the parameter is pointing to? That is the kind of stuff that I want you to tell me when a register gets changed. Is that okay? Does everybody know, my expectation of, what to comment in a question like this? Okay? So one thing you can do is to practice, okay? You can take my source code of Fibonacci, okay? Because that one is already done. You already have that source code, and do this to that particular source code. So that will make you think about, what each register has in that particular program along the way. I know that program is a little bit longer than this, but that also gives you more opportunity to practice. Okay? All right. So that's the first thing, okay? Because the question says you have to do two things. This is the first. The second one is to disassemble this. In other words, what is the C code corresponding to this assembly code? So give me the C code. Yes?
There's JZI as well. You said you're going to go back to it.
Right. But that's only needed when I need to disassemble it. Because JZI and if does not change a register or a memory location. So there's no need to comment it, as far as C concepts are concerned when we are just updating registers or memory locations. But now that we are disassembling, now we have to kind of, say, okay, what does this look like, after we disassemble it? Okay, so we start with the prototype. Okay, the first question is, do you think we are returning any particular value in this case? I mean, it's possible that register A, which has, which has a parameter P in it right now, is potentially the return value, but the C prototype is already telling you it is a void function. So you can just copy from the prototype that is given to you. So you can now say, okay, this is a void function. The name is node append, and the types are already given to you as well. So pp we know is a pointer to a struct node, and then p is really just a struct node pointer. That is given to you in the prototype. So if I give you the prototype, you can just assume the prototypes. You don't have to come up with your own prototype. So once we have the prototype or the parameters determined, so now we need to look into this and go like, okay, what is it doing? Well, let's see what it's trying to do here. Increment A, doesn't really do anything that seems to be reportable in C. Load A, indirect A into C. Okay, so we have PP stored into register C. So that by itself is not reportable either, okay? But how we use C over here seems to be important, okay? We are using the AND operation to set or reset or clear the sign flag and also the zero flag. But the conditional branch right after the AND is only focusing on the Z flag. So we know the sign flag is not important in this case because we're not checking for it. So that means this part here, and then if the Z flag is set, it is going to end if, which is at the end of the subroutine. So right now, what kind of C code are we? Can we deduce?
If C is not equal to 0.
Nope, C is not visible in C. Okay, that sounds really bad. Register C is not visible in the C programming language. How about that? Aha, very good. Okay, So remember, when you convert this code into the C programming language, okay, the registers are invisible. So you cannot use registers to document what the program is doing when you convert the program into a C program. Does that make sense? Yep.
Can we make a variable and make it equal to C? Oh, well, that's just too much work in mind.
Well, then the type of that variable C is going to be very interesting because sometimes it's just a single pointer, sometimes it's a double dereference, and so we don't want to see the registers. Okay. Hmm? Well, you can make it a union. Okay. Has the concept of union ever taught? No. Okay. Let's not touch that. I cannot do the MC Hammer thing. Yeah. Okay, so we're basically saying if PP, then we do something. Else, do absolutely nothing and return. Okay? So this construct, okay, is only making use of the code from here and this label here. Are we doing okay so far? Okay. So let me use some color coding here. This is the blue stuff, and this is the blue stuff here. Okay, so what if PP is non-null? What if it is not zero? Well, then we have to focus on the green stuff. Okay, the green stuff is right here. So if we look at the green stuff, we already have figured out what it's doing, right? So all the green stuff is going to do, okay, so we're inserting the green stuff in here, is really just the last one. Yeah, exactly. Whatever PP is pointing to is getting whatever P is. That's it. That's the entire function. That's how we append a node to the end of another node. Are we doing okay so far with this? Yep.
Is a double pointer redundant?
What do you mean by redundant?
Well, it's a pointer to a pointer, so you don't have to say it's a pointer to a pointer.
You do it.
Do you?
So, okay, so that's exactly. Okay, so the reason why we have a double pointer here with PP is because if you have a single pointer, the C compiler will complain about it.
You have to tell the compiler how many jumps to get to the non-pointer.
Exactly. Because, okay, so let's look at this assignment statement here. There's only one assignment statement. The idea of a strongly typed programming language is the type of the right-hand side has to match the type of the left-hand side. If they don't match, the compiler will complain and go like, you cannot do this. Okay? So, from that perspective, if PP is a pointer to a pointer of a struct node, one level of dereference will give you a pointer to a struct node. Right? When you look at P, it is a pointer to a struct node. So the types do match between the left-hand side and the right-hand side. If you remove one of the asterisks of PP, then whatever PP points to is now a struct node. But P is still a pointer to a struct node, and you cannot assign, the right-hand side cannot be a pointer to a struct node, but the left-hand side is an entire struct node. That does not work in C. Yep. So it is necessary. The double pointer thing is necessary because of type checking. So are we good with this one? Yep.
So that idea is kind of reflected in your assembly as well, right? Because you loaded address of PP and then you loaded P.
So in the assembly code, by the time we get to the store instruction, the only store instruction, register A actually has parameter P stored in it. And then register C, which is indirect, used in the indirect way, has PP in it. So what we are doing is we are not storing P to PP, we are storing P to whatever PP is pointing to.
Because the store actually dereferences as well. Because the store instruction dereferences.
Yes, because every time you see a pair of parentheses, that's the visual cue of it is being dereferenced. And there are only two instructions that can dereference something. One is load, and the other one is store. So those are the only two instructions that can dereference. One is for storing into RAM, the other one is for reading from RAM. So are we good with this question in terms of the answer and how the answer was derived? Okay. So once again, you can do this. When I give you the code for the tree homework assignment, you can do that with that code. It's going to be a little bit lengthy, it's going to be a little bit messy, okay? But it is good practice, okay, to kind of go through that and then figure out what is the logic of the code, and also what is in a register after each update. All right. So shall we move on? Okay. So moving on to question number 2. So question number 2 gives you the actual C code, and you have to give me the assembly code. So we'll read the question more carefully. Okay. Implement this code in TTP-ASM, which is Text Toy Processor Assembly Language. Make sure your implementation is not sensitive to any ordering or positional changes of members in the structures. In other words, if I decide to change the structure, okay, and reverse the order of the two members, your code should continue to work, assuming the labels are updated accordingly. Which means don't make assumptions that V is the first one and N is the second one. Okay, is that okay? Does everybody understand what I mean when I say, your code should not be sensitive to the ordering or the positional changes of the members of the structure? Yes? Okay. Furthermore, your implementation must follow the ordering and meaning of the C code as closely as possible, which means if there's a shortcut to do something, do not use the shortcut. Your code should resemble the logic of the C code. In this case, it's pretty hard to kind of do it the shortcut way, but in some other cases, like in the swap subroutine, there's a shortcut that you can only do in an assembly code, but you cannot use that approach in C code. All right, so let's go ahead and get started with this. So the assembly code is going to start with node init, because that's the entry point. So the name of the subroutine becomes the label of the entry point. And I'm going to define some labels. Now, you do not have to do that. If you say I can maintain the position of a register on the stack and I can just use that, that's fine. Okay, but I'm going to define some labels here. So I'm going to define return address as 0, and I'll define P to be return address 1+. Okay, that's just a usual thing that I do, but you are not required to do this. Okay, so as long as I can read your code and you can keep track and maintain which register has what, and it is correct, I will still give you full credit for that. All right, so now I need to access P first. So there are several ways to do this. Okay, for those of you who do not like to have the longer way but more mechanical way to do things, you can just kind of do a CPR, AD, and then just manipulate, the registers, to get to the places that you need to get to. But I'm going to go for the more mechanical way. So the more mechanical way is to do LDI. We can use any one of the registers A, B, and C, or C. So LDI A with P, add AD. So that will give me the address of parameter P in register A. And then I need to do a dereference because I'm not interested in the address of P. I'm interested in the parameter P itself to see where there's null. So I will do LDAA, okay, and then do an AND AA. Okay. So the AND AA is checking whether parameter P is null or not.
So you do JZI and
Yep. JZI and if. You go like, hey, that resembles the other program that we already looked at, and you'll be correct about it. Okay, so we JCI to end if. Okay, so for those of you who say, okay, but I want to code this in a structured way, which means I'm dealing with a control structure, you can do that. Okay, so you can basically say end if right away over here, And then you have the return code. The return code is LDAD, increment D, and then JMPA in this case. Register A can be used in this case because it's a void function, which means the caller is not supposed to assume register A has some kind of useful return value from this subroutine. So after this, now we can do the insertion thing, okay, and say, okay, this is the kind of stuff that goes in between the JCI to endif and endif the label itself. So now we need to implement the two statements, the two assignment statements that is inside the conditional statement. So when you're doing this, you can basically assume that a certain register already has P, so it's okay. Okay, it's okay to optimize a little bit. So what we need to do now is to get to member N, and then we have to get to member V. Now remember, the assumption is, if I change the ordering, if I change the structure, your code should still work. So do not make any assumptions, okay? Do not just say, oh, you mean, both bytes pointed to, the byte that is now pointed to by P needs to be a 0, and then the next byte needs to be a 0 too. Do not make that assumption, because I might insert additional members into the structure, and this code is still only supposed to initialize the members N and V. Okay, so do not use that approach. So what you need to do instead is to do an LDI, pick another register, say B, and load it with node underscore N in this case, because that's the first member that we need to initialize. And then you say add BA, because register A has pointer, which is pointing to the base of a structure. If you add the offset to member N from the beginning of the structure, now register B has the address of member N. Okay, once we have that, we can put a 0 into it. Good thing we have 3 registers available to use. Okay. Mm-hmm.
Based on the fact that we're dealing with a structure that's already defined somewhere else, we can assume that those labels all exist.
Mm-hmm.
Node
Yes.
N and node.
Yes. So you can assume the labels do exist, and you can also assume the labels reflect the correct offset from the beginning of the structure to those particular members. But what you cannot assume is the position of those members remain the same as they are given to you.
So now in this next step, you have to do
Yep.
the same thing that you did to get to node N in order to get to node V. You can't just
That is
go
correct.
from N to V.
Yep. Because the idea is, if I decide to change the C code, if I decide to change the structure in C code, I want to just be able to change the label definitions, and then the rest of the program should continue to work. And that's it. Well, I mean, the LDIC 0 doesn't have to be done again. Is that the question? Yeah. Okay.
Unless there's an interrupt?
Huh?
Unless there was an interrupt?
No, an interrupt would not be a problem, because an interrupt is supposed to restore the content of all the registers.
Oh, okay.
Yeah. Mm-hmm.
Why did you have to OUIC 0 in the first place?
Because register C is uninitialized.
But you're just storing the.
Huh?
But you're just doing store.
I'm going to change member N of whatever PTR is pointing to. So I cannot just store register C to what B is pointing to, because otherwise, I don't know what is in C, right? Yep.
You have no preference on labels, like the names of labels?
Nope.
Okay.
As long as it is not offensive.
Okay.
Well, as long as it's not too offensive. So, label names like mildly offensive, like damn it, I'm going to fail this class, is okay. As long as it's underscores between every single word. Or use the camel casing. All right, so let's see. Yep, so that's the only part of this question.
2-minute voicemail in only 10 seconds.
Time compression. All right, so how many questions have we answered? We answered 2 questions, right? Okay, so there's question 3 here. So there's a listing, the following question rely on the following C code definition. So we'll go over the C code definition first. I think this resembles a little bit of what you guys have to deal with, except there's a little bit, there's something that's kind of crazy here, okay? You know how to deal with this, right? Whatever PP is pointing to, check whether that is no or not. So this is not a problem. This one here looks really bad, right? Because we are looking at the address of member N of the structure that is pointed to by PP. Okay? We'll deal with that, okay? When you look at it, it looks really bad. The idea is do not get anxious because it looks bad, okay? Instead, you rationally approach this and go like, where do we start, okay? Work on this step by step. That is the key, okay? The other one is pretty easy. We're just passing along whatever P, parameter P that I get, I push it, and then whatever PP I get, I push it again, and then call, okay? The partial and probably incorrect implementation is as follows. In other words, fortunately, you're not going to write the entire thing. Unfortunately, I'm going to write a faulty implementation of this subroutine, and your job is to fix it. So I'm not sure which one is worse, okay, to say that, okay, go ahead and implement this, or this is my implementation. We know it's probably wrong. Go ahead and find out where it is wrong and fix it.
But you say probably, that means it might not be.
Yes.
Thank God we get 2 hours for this exam. Thank God we get 2 hours for this exam.
You have 2 hours for this exam, yes.
We have 2 hours for this question, right?
Okay. So question number 3 or 5 just makes use of what we saw. So it refers to listing to using the following. Refer to listing to using the following space. List the line number of each part that is incorrect. Explain why it is incorrect and state the correction. Do not worry about the missing portions labeled T0D01 to do. Okay, it's to do 1 and to do 2. Okay, so ignore those 2 sections. Okay, so there's a section here. Okay, so to do 1 is here, to do 2 is over here. So you can just ignore that. Okay, in other words, that part is used to implement the conditional statement. You can assume that that is specified later. So there's no need to fill that in for this particular question. So this question is only concerned about the code that is already given to you in listing to, which is this portion here. And if there's something wrong here, you have to fix it. You have to tell me what's wrong with it and fix it. Is that okay? Are we good? So how do you get started? Well, you get started by comparing the assembly code with the C code so that you can identify, what the discrepancies may be. Okay. So that is a little bit difficult because I can't easily display both the C code and the assembly code at the same time, not using this particular method. So I'm gonna have to use a separate tool to help me do that. So I'm going to open the same file, but using a different program. That one is just for display purposes, like that. And I need to structure it. Let's get rid of this portion. I'm trying to get rid of, oh, there we go. Yep. How do I get rid of the bar on that side?
Is it the top left button in the top menu bar?
Oh, yep. There you go. Thank you. And then we scroll to the question. This is already the question that we want. And then we'll magnify a little bit. There we go. All right, so we put it here. And then we have to resize this portion. So we want this part to look at the C code, and then this part to look at the assembly code. And now we can kind of go back and comment on which line is wrong and how it is wrong. All right. So we are going to start with the parameters. Okay, according to these labels, P is 1 byte away from where the stack pointer points to, and PP is 2 bytes away from where the stack pointer points to. Is that correct? That is incorrect. They're reversed. So we have to fix that. So to fix that, you have to indicate on line 52, okay, PP should be defined as 1, and then on line 53, P is supposed to be defined as 2. So that's what I'm referring to. You have to tell me the line number and the correction to that line. Okay, so that's done. What?
I guess I'm just misremembering, but I thought that the final parameter was pushed first.
The last parameter is pushed first, and therefore it has a higher address. It is further away from where the stack pointer points to. Remember, the stack is, it grows backwards.
The stack pointer is lower.
Yep. Yep. Okay. So now, we look at, once we are done with the definitions of P and PP, so now we look at the rest of the code, okay? We load a PP, which means A is now the offset from the stack point, where the stack pointer points to where the parameter is, add AD, so that seems okay. So at this point, A has the address of PP, and then on line 56, A would end up with the parameter PP itself, and then on line 57, A would end up with whatever PP is pointing to. So they're all correct up to this point. And then on line 58, we have a problem, because you cannot compare a register with an immediate. Such a comparison does not exist. That instruction, it does not support this kind of operation. Compare can only compare between two registers. Yes? 54? Oh yeah, it should be LDI. Thank you. That's a good catch. I missed that one. So line 54, we have LDI, A with PP. Very good. And then on line 58, okay, we need to split that into two lines because we have to load some 0 into a particular register. Or what else can we do about it? Can we do something else about this?
And then JZI.
Well, what we want to do is to see whether it's 0 or not. We can use the AND, and what are we ANDing? And A with A. Yep, okay. But then we have to change line 59 too. So line 59 is going to, it needs to go to the else case. When do we go to the else? If it is 0. So we have JZI to else. Okay. All right, so what about line 61? Line 61 goes to end if. That is correct because we have the else branch, which is represented by to do to. So we want to jump around the else branch. So jumping to on line 61, jumping to end if is okay. Line 62, the else definition, the else label definition is at the right place. And then on line 64, the end if label definition is also at the right place. But don't relax yet because we got 3 more instructions to go. Line 65 is going to load the return address into register B. That's okay. Line 66 is incrementing the stack pointer, which is okay because we're deallocating the return address from the stack. Line 67 is a problem because it should be just jump and not JMPI. Okay, so we have another correction here, which is line 67 is supposed to be a JMPB and not a JMPIB. So are we good? Yep.
What's the difference between these? Why do we want JP and not JPI?
The difference, okay, so there are There's the short version of the answer and there's the long version of the answer. The short version of the answer is JMP uses a register. Whatever the register has specifies where we are continuing execution. JMPI, on the other hand, expects probably a label, but any expression will do, okay? And we are just continuing execution, whatever the expression turns out to be. Whatever is the value of the expression is where we are going. One is runtime dependent, okay? JMP is runtime dependent because the value in the register is runtime chain. It's modified at runtime. The other way, which is JMPI, has an expression that is determined at assemble time or critical compile time. So that one is static. But when you look at the code that they generate, the opcode that each one generates, and also look at how the microcode, in the assembly, in the architecture is implemented, that will also show you how they are very different. Okay, so I do recommend the long version, which is looking into the microcode and find out, how the pathways are different, because that will give you a really thorough understanding of how these two instructions, even though they look alike, but they are actually quite different. Okay. Any other questions about number 3? Because that's really the answer of number 3. No questions? Okay. So if there are no questions, we're going to move on to question number 4. So question 4 says, refer to listing 2. Use the following space to write the code otherwise needed to replace to-do 1 in the function. Okay, so now you have to implement, but not the entire thing, just whatever is supposed to go into to-do 1. Okay, so what we need to do is now to look at the assembly code and also look at the C code. And can someone tell me what line of C code is corresponding to to-do 1? To-do 1 is basically just a placeholder of the assembly code that corresponds to a particular portion of the C code. The node add list call. Yep. So this is this particular call that we have to implement now. So it's the ugly one. Okay. It seems to be the ugly one, but it's not actually too ugly. So let's go ahead and work out that one. Okay. So we move on to question number 4, which is the right space to put down this answer. Okay. So now, if you want to, you can always just kind of repeat what you're trying to implement. Node add list, and then we have the address of that points to n, okay, comma p. Okay, so this is what we need to implement, and at this point, I don't need to look at the C code anymore, so now I can have a little bit more space for the entire code. Okay. All right. We can assume the labels are already defined. So we have labels defined for the parameters, and we also have labels defined for the offset to each member inside the structure of node. Okay, so we can assume those labels are already defined. So we'll deal with P first. P is the easy one. So let's push the last argument, which is P on the stack. So you can just do a LDI A P add AD, and then do a LD, AA, decrement D, and then STDA. Okay, that will push P onto the stack. That's the easy part. Now we get to the more difficult part. So with the more difficult part, it looks really ugly, right? We have a dereference, and then we have a pointer thing with a member, and then we take the address of that whole thing. So it looks really bad. Where do we start? If you are given an arithmetic expression that has a lot of parentheses, a lot of nesting of parentheses, where do you start? The innermost portion, right? So same thing here. So the first thing we do is to say, we are not interested in the address of parameter pp. We're not interested in parameter pp itself. We're interested in what pp is pointing to. Okay, so we need to get that first. So how do we get that?
So LDI.
Okay, so we're going to start over here because it's going to be a little bit long. Go ahead.
LDI.
We can use A.
Yeah, A with PP,
Uh-huh.
and then LDAA.
Don't forget the add AD, okay? Because you have to add the stack pointer to the offset to actually get to the address of the parameter. Okay, so don't forget that. Don't forget that. So right now A has the address of PP, right?
So now you can do LDAA.
Okay, so we have LDAA. So now we have parameter PP, right? And we need to dereference that. So we need to do it again. Okay, so it would be very helpful if you add your own comment, so that you remember what register A has at this point. Okay, I'm not putting it here, just so that if I give you this document, you guys can do it on your own. Okay, that's an exercise. So right now A has parameter PP. A now has the address or the thing that is pointed to by PP. Okay, so we got this part done. Okay, let me just use some color coding here. So we can use blue and say that this chunk here, which is in blue, is implementing this portion here. Okay, so what are we doing with A? Oh, by the way, what is the type of A at this point? It is a struct node pointer. Okay, very good. Because the first parameter of node at list is struct node pointer to a pointer PP. So by dereferencing PP only once, we still have a pointer. So what is in register A at this point is a pointer to a struct node. Are we good so far? Okay. What are we trying to do to that pointer? We're trying to access. Yeah, go ahead.
Get to like these ends.
We're trying to get to member N of the structure that is pointed to by this thing in blue. That thing in blue is in register A right now. Yeah. Okay. So the other way to put this is register A is now pointing to the first byte of a struct node, of which we only want to access member N. So what do we need to do? Add the offset. Okay, very good. So what code do we need? LDI.
LDI. B and N.
Pick another register. We can pick B. And we'll use node underscore whatever the member is, N in this case. And then we'll add.
AB.
We'll add BA or BAB, doesn't really matter in this case. So we can add AB. Okay. So now you have to ask, what is in A at this point? A is not a member. It is the address of member N of the structure that is pointed to by a pointer that in return is pointed to by parameter PP. Then we have to take the address of, or do we? We are done. That's it. It only looks more complicated than it is because in C and C++, we always get to the value. If you don't do the ampersand, we are specifying a value of something. But in assembly language, you always get to the address of first if you want to get to the value. So we are already at the address of the member at this point. We're done. Register A has what we want. So what is left to do is to push it on the stack. So I'm going to use some color coding here. These two is basically doing the rest of what you need to specify as the first parameter. So the rest of it is relatively less important because we just have to push it. So now we have decrement D, std a, okay? And then you have to push the return address and call the subroutine, which is decrement D LDI A dot 5 plus std a jmpi to node add list But we are not done yet, okay? Because the caller is supposed to deallocate the arguments. So when we come back, we have to do to increment d in order to deallocate the arguments. Now, obviously, certain things are more important, okay? If you forget about these two, increment these, points will be deducted, but not a whole lot, okay? Because those are not exactly the meat of this question. The first part over here, just to push P on the stack, there are some points associated. But the main part of this would be the part in blue and also the part in green. So are we getting this one? Yep.
So when you add A to B, that adds the
It adds B to A. Uh-huh.
Yeah, B to A. It adds the displacement from where PP is to node N.
Okay, so let's go back and look at what register A has when we get to the add AB instruction. Register A is now a pointer to a struct node. In other words, it is pointing to the first byte of a structure already. B, on the other hand, is the offset from the beginning of a structure to the member end. So when you add the offset to a particular member to the base address of an entire structure, now you have the address of the member inside that structure. And that's what we want, because that's what this expression in C is specifying.
Oh, that makes sense.
Is that okay?
Yeah, no, that makes sense.
Yep. And I will send this document to you in PDF, or if you want to, I can send it in Zerno format as well. You can download and install Zerno in Windows if you want to. Or I can just send it to you in a PDF, and you can use whatever tool you want, to kind of add more annotation. If you want to type this up, in a text editor, and then add your comment, in a text editor, that's fine too, okay? However you want to do it, I will give this to you, okay? And you can bring that with you on the day of the final. Yep.
You don't have to load A to A because it needs to be dereferenced. And it already has the and right there, right?
The ampersand says I'm only interested in the address of the member. I don't really care about the value of the member. By the time we get to the add AB instruction, we already have the address of the member. So we good? Okay. So did you guys see how we do it step by step? Okay, it looks ugly, okay, but you do it step by step. Okay, you don't look at the whole thing and go like, oh, this looks so bad, I can't get started with this one. Yes, you can. Start with the innermost part of the parentheses of the nesting. Okay. All right, so let's move on to the last question. All right. So the last question says, refer to listing to using the following space, write the code otherwise needed to replace to do to implement the implement the function at node at list. So this is easier than the first one, because this one is really just, we're just passing stuff along, okay, to the subroutine. All right, so I need to resize Zerno to look at the code. Okay, so the first thing is, where is to do to? You guys cannot see it. I'm gonna have to scroll a little bit. It is the else statement, correct. But I do want to show you in assembly code where that is. So in assembly code, to do to is over here, which is right between the else label and the and if label. Okay, and that is corresponding to the call of node append. Okay, and
Didn't we already do that in the previous question?
no, the first question was to
We did the
disassembly. Yep. So this one is really just to implement, the call to add a node append. And I would say this may be the easiest part of the whole test. Yes? Maybe. Okay.
Deallocate to local variables, push them, and then
Yep.
the return address, and then you're done.
So LDIAP add AD LDAA. Oops. and then push it, right? Decrement D, STDA. That's pushing P on the stack, which is the second argument. And then we have to push PP on the stack. LDI, okay, so let me continue here. LDIA with PP, 1 plus. Okay, why do we need that 1 plus? Yep, because the stack is now one item, has one item more than at the entry point of the subroutine. So the offset to everything that I put onto the stack earlier is now 1 off. So I have to remember to add that 1 byte. You had a question?
No, that answered it.
Okay.
And you can just do that in line like you did, right?
Hmm?
Do LDI. You can do multiple LDIs in line.
What do you mean by?
The PP1 plus.
Yes. So LDI or anything that ends with an I, including JMPI, you can use an expression for the immediate thing. So that as long as it is resolvable at assemble time, it's okay. So it cannot depend on the value of a register because it cannot refer to a register as an immediate. Because what the immediate really is the next byte, the byte that is next to the opcode. So we have add AD, okay, the rest is the same, okay, LDAA, decrement D, STDA. So now we have 2 arguments pushed on the stack, and then what is left is to push the return address. So with that one, it's decrement D, LDI, A dot 5 plus, STDA, JMPI to the subroutine, which is node append. And then when we get back, we have to increment the stack pointer twice to deallocate the arguments that are on the stack, and we are done. So including the explanation and actually handwriting the answer, we still have how many minutes left? We still got 15 minutes left. So it's not about, so the amount of time it takes to write it down is not the bottleneck. The bottleneck is, the application of the concept that you have learned in this class. Are we good so far? Are there any questions? Any questions about the concepts? Because the concepts, is the most important part. Yep.
I mean, can we go over the part where you discussed the offset on the stack, the 1 plus argument for PP when we were putting it on?
You mean here?
Yes.
Okay, so by the time we get to, okay, let me point in the on the screen so this way people can. Okay, so we are talking about this instruction. So by the time we get here, we would have pushed one more thing on the stack already because of this decrement D, right? But remember, where is PP? Where is the parameter PP? Or what is PP the label representing? But what is it representing? I know it's defined as 1, but what is it representing?
The first parameter to be pushed.
It is representing the offset to parameter PP from where the stack pointer points to at the entry point of the subroutine. Okay? So now the question is, has the stack pointer itself changed from the entry point of the subroutine to this particular instruction, which is LDIA, PP1 plus? Has it changed?
Yes.
And how has it changed?
There is now another number on this.
Well, I don't care what is on the stack, but the stack pointer is now 1 byte pointing to one byte lower compared to the entry point, right? So if PP is the offset to parameter PP relative to where the stack pointer points to at the entry point of the subroutine, don't you think, we have to add one now because the stack pointer itself is is basically one less than what it was at the entry point of the subroutine. So this 1 plus is to compensate for this decrement D. Yep.
Do you not use labels? Say use P0 and then PP P1 plus as like labels before, and then just use that. So
That's what we're assuming we have.
Yeah,
Oh,
because
okay,
it's
okay,
already
okay.
defined. Because it's already defined. The
Okay,
code,
Okay.
yeah, the code that was given to you already have these things defined. Even though they were erroneous, they are assumed to be here.
Okay, that's fine.
Yeah, so you can make the assumption, during the final exam that parameters have labels defined in assembly that correspond to the offset from where the stack pointer points to. And then with structures, each member of a structure has a label defined that is the offset of that member from the beginning of a structure. You can kind of assume all of those labels are already given to you. They may be erroneous, like in this one, and I will ask you to debug it, but the meaning of the label is always going to be the offset from the stack pointer to that parameter, or local variable if it has one. So yep.
When we're getting ready to return over here and you do the LDI A 0.5 plus, since we're always using LDI, ST, and JMPI, is it always going to be 5 plus typically?
Well, the question is, why do we have 5 plus?
Yeah, do you know why it's 5 bytes, right? Because you're using those instructions, right? So LDI is 2, store is 1. Right?
And the JMPI is 2.
Right.
So you have 0, offset 0, okay? So the 5 is basically an offset of where we want to return to relative to the beginning of the LDI instruction. So once again, we're dealing with offsets. So LDI itself is at offset 0 and 1 from LDI itself. ST is at an offset of 2, and then JMPI is at an offset of 3, but JMPI has 2 bytes. So we have 3, 4 here. So that means the increment D instruction, the first one, is at an offset of 5 bytes away from the beginning of the LDI instruction. And that's why we have a .5 plus, because the dot is representing the address of the first byte of the LDI instruction.
So since we're typically going to use just those instructions to do that, it'll pretty much always be 0.5 plus.
Assuming you have the same sequence here.
Right.
If I switch the order between the decrement D and the LDI, then it'll be 1, 6 plus. Yep.
So I was going to ask whether how much it matters where you put the decrement D, like in that third column, for example.
Say that one more time. Sorry.
What order you put decrement D? How important is that?
What order? It is not important. So the ordering between the decrement D and the LDI is not important because they do not depend on each other.
Right.
One changes register D and the other one changes register A, but it does not refer to register D in any way. So they can be done in any order. But if you switch the order, then the offset from the beginning of the LDI instruction to where you want to return to would be changed. So that's why the .5 plus need to be changed if you switch the order around. The ST instruction has to be here because the ST instruction depends on D and A. So the ST instruction you cannot reorder the ST instruction to be before any one of those 2 other instructions. So ST has to be here, and then the JMPI has to be here too, because until I save my return address, I cannot go to the subroutine because otherwise the subroutine would not know where to return to. So the ST and the JMPI have to be here in this particular order, but the decrement and the LDI they can switch. But when you do switch those 2, you have to remember the offset would also change.
Okay, so you can't in the other 2 columns you can't move decrement D up because you are adding D to A.
Because you cannot switch this decrement D any further up because the ST instruction here, for pushing PP on the stack, that relies on D. So if you double decrement D first, then you would be overwriting the same location twice. Because the first time you will overwrite it with is PP, and then you immediately overwrite it with the return address.
Well, yeah, I meant whether you could, like when you're doing the PP one, whether you could decrement D before loading in, Like,
I
yeah,
see.
that, yeah.
So these two can exchange. So the LD and the decrement D, these two can exchange without any ill effect.
But not all the other ones. Like, looking further, like how far up?
You mean this one?
Yeah.
This one can only go up here.
Okay.
Because if you go up any further, then it will change the value of register A, which is supposed to be the address of PP.
Right.
Yep. So you cannot move this decrement D any further. You can only move it up by one. Yep.
So when you're pushing the return address, you can also just create a label, right, after the JMPI instruction.
You can.
Push that.
Yep. You can use a label definition right here and then refer to the label here. But we move away from that method because that would basically every time you have a call or every time you invoke a subroutine, you need a label. So now you have to come up with a systematic way to come up with label names in order so that you remember which one is which one and do not reuse labels, reuse the wrong label. And this way, there's no confusion. I mean, this is pretty clean. We don't need to define a new label every time you call a subroutine. Okay. Any other questions? Yep.
I guess I'm not sure if I'm misremembering, but I thought when we are writing a whole program in assembly,
Mm-hmm.
we start with no op or whatever, but then we decrement D first to allocate space for
In main.
in main.
Yes.
Right? So why do we do that? Okay, is that because we're
Because main it's almost considered like a function.
yeah.
So all local variables are allocated from the stack.
Right. Okay. Yeah.
So when main itself has a local variable, we have to allocate that from the stack too.
So that when you get into a subroutine, you're already down to where you need.
Mm-hmm.
That's why you wouldn't decrement D again before loading it in.
Say that again. Before you don't have to decrement D before you load what?
Well, like how we were doing, loading in PP into A and then adding the stack pointer. So the stack pointer is already pointing to a space for this local variable that we're pushing.
So at this point, because we are already in the subroutine,
Yeah.
assuming all of the other, the implementation of the rest of this subroutine is correct, the stack pointer will now be pointing to the return address again. So we can make that assumption that at the beginning of each statement in C, the stack pointer is pointing to it's the same as at the entry point of the subroutine. So any other questions? So I'm gonna save this file, okay, as a PDF, and I can send the PDF to you, and then you can use whatever tool you want, okay, to annotate it, explain it your own way, or just toss it. Yep.
How many finals do you have in your folder, like for the 4 semesters, or like semester before that?
They are basically just variations of the same questions.
Oh,
So they won't help you, in terms of getting
Okay,
some exposure to different questions.
so just variations. That's it.
Yep. Yep.
So the obligatory question is this going to be what this semester's final looks like, pretty much? Do you think?
I do not know yet. that's a difficult question, because I don't make up the questions until like the last minute.
So I was doing another one and there was no mention of structs. Because I was doing another final and there was no mention of structs.
Yeah, that's because depending on the semester, sometimes I cannot get to concept of structs, or students did not have a chance to work on a homework that has to do with structs. But this year we did. This semester we did. Yep. But structs are important. Okay, I know we are running out of time, but I do want to show you one thing, just one thing. Okay. It is probably accessible from the internet, so you guys can access it too. It's arccis.net _name. Okay. So these are the things that I have done in the past. And this is the real-time kernel. All right. So I want to show you this, because I wrote a small, real-time kernel. a real-time kernel is kind of like a miniature operating system. It doesn't have a file system, doesn't have a user interface of any kind. All it can is to manage threads. Okay, so this is a thread management type of thing. So with this RTK or real-time kernel, you can have a multi-threaded program running on the same kind of processor as the Arduino. So just think of the Arduino, but being multi-threaded, capable. And it also has priority queue, which means depending on which you can prioritize. Okay, you can basically assign a priority to each thread, and then low priority threads do not get execution time until all the higher priority threads are done, or say I'm waiting for something. Then the low priority threads get execution time. Okay, so that's the whole purpose of the real-time kernel. I'm not going to spend too much time to explain how it is implemented, but I do want to show you the API or the application program interface of the real-time kernel. This is C prototype, right? It's a void function, RTK thread add, which means you're adding a thread to the real-time kernel. You pass it a pointer to a thread structure. You pass it a pointer to a queue structure. You give it a stack pointer, which is just pointing to a chunk of memory where you have allocated to be the stack of that particular thread. You give it a function, a pointer to a function to start the thread, okay? And then you can potentially give it also a parameter to start the thread, okay? So you can pass all kinds of information when you start a thread. But this is C code, okay? It is designed for C. It compiles in GCC for AVR. And the C compiler says, okay, as long as you tell me this is what the API looks like, it can generate the code for that. And then the thread is a structure. It is defined in one of the header files, but it is just like a normal C structure definition. Okay, it has got some pointers, has got some room for saving all the registers, blah 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 blah. Okay. But now the question is, how is the real-time kernel implemented? In other words, what about the code that is corresponding to all of these subroutines? RTK thread suicide, well, the thread can kill itself. That's why it's called suicide. And there's also a thread kill, which means I'm not the thread that is getting murdered. I'm murdering the other thread. So there's a different function for that. Okay. So the question is, how are these subroutines implemented? They cannot be implemented in C or C++ because you need direct access to the registers because you have to save all the registers. And then the kernel has to say, oh, this thread now is going to be suspended because it's waiting for something. And then which thread is now ready to run? Ah, that one. You go ahead and run. That cannot be done in C. So the source code So the source code of all of this is, guess what? Written in not TTP ASM this time, because it's a real architecture, okay? It's a real architecture. It is all written in assembly. So it's all written in assembly. Let me see if I can actually find the code for that. Okay. But this is the application, because I want to kind of show you guys what the applications are. And I want to find RTK something. Ah, it's not here. I know it's... There we go. This is the assembly code of the real-time kernel. And we got push because it's not a true RISC type processor, so we got push instructions. We have std instructions, which is kind of related to our store instruction. Let's see, we have LDI. Okay, so LDI is directly copied from that particular architecture. There's LDS, which is a little bit different from our LD. There's RJump, which is relative jump. Okay, it's not the same thing as JMPI, but very close. Move is CPR. Okay, copy register. So the entire kernel is written in assembly language. How big do you think it is? How many bytes do you think the real-time kernel takes? It's a small, tiny little, operating system that is capable of multi-threading. It also has time slicing, which means, if a particular thread says, I want to hold on to the execution time and I'm not giving up the processor, the real-time kernel kicks in and go like, time's up. And then it will look up the same queue, the same priority queue, and see if there are any other threads ready to run in the same priority queue, and therefore the name queue, because you have to go around and say, okay, his time is up. What about you? Are you ready to run? Okay, now you get time. Okay, so it can get all of this stuff done. The footprint of this real-time kernel is 2 kilobytes, as in 2,000 something bytes. Because you're talking about devices that only has 8 kilobytes as its limit of how much code you can put into it. So 2 kilobytes is already taking up like a quarter of the code space of that particular architecture. So this is the reason why I teach this class the way I teach this class. Why I emphasize, okay, this is a C structure. How do you interact with a C structure in assembly code? This is why. Because this is the kind of thing that you might need to do if you get into embedded system development. Because there's no operating system. Okay, this is a new architecture. It's a very small architecture. You cannot run Windows. You cannot run Linux. There's nothing, as an operating system. And then you say, but the application that I want to do it needs multi-threading. What do? Well, if none is available, you write your own real-time kernel. But in order to write your own real-time kernel and still continue to be able to write the rest of the application in C and C++, you need to understand how code is compiled from C into assembly so that your assembly code can interact directly with the rest of the C code. So I hope this gives you a context of the kind of ordeal that you have gone through this entire semester. Yep.
How does the assembly get to RAM? How does it get to RAM?
How do you get to RAM?
Just putting it.
Okay, so that's also an interesting question. How does the assembly language get into RAM, or where it's stored? In this case, this architecture is called a Harvard architecture, which is a little bit different from a von Neumann architecture. The code is stored in flash memory, and then the RAM is only for the stack and the local and the global variables. So you have to flash program this thing onto the chip on the circuit board.
Oh, okay.
Yeah, there's a special connector that you hook up a dongle to, and then there's a special program that you run in order to flash the flash ROM on the microcontroller unit to program it. So the code that you see here is going into the flash portion of the chip, but it has RAM as well, but that's only for storing variables and the stack, and everything else is in RAM.
Oh, okay.
Yep.
So you'd have to do that for each computer you wanted to run that kernel on that?
Yes. So if you mass produce these things, you can actually tell Intel, not Intel, Atmel, which is the manufacturer of this chip, you can supply the base code that you need to program into every single one. So when they roll out of the factory, they can pre-program those, with the code that you want to be on those chips. So that's only good if you need to mass produce something and then the code is already stabilized. Because otherwise, then you get all the chips, then you have to solder the chips onto the circuit board, power up the circuit board, and then use a special dongle to program it. All right, well, I guess our time is up. So I'll be over at the lab for those of you who want to ask questions, or I can use that time to kind of work on the key to the homework assignment. Beginning of the class. It is 10:15 to 12:15.